All right, 3 out of 3, the third video in our switches set. So we are going to look at, we've covered 2 other videos previously. The first video we talked about some basic kinds of switches, 2 really main ones, which are a momentary switch and our latching switch, and then a special case, which is our tilt switch. Then we talked about why we need a pull-down resistor in that switch and the right way and the wrong way to attach a switch to anything that's trying to read a signal. And now we know that we have this circuit that we can use, and we're going to figure out why that circuit works the way that it does, and kind of look at some voltages and currents, do a little bit of circuit analysis on this. So we have this circuit that we made last time, and we're going to focus on this top circuit here, and I'm just going to redraw that really quick so that we can have a clean slate to work from. So right here, we have our digital signal, again, DX. That's our digital input, regardless of what pin that is on your Arduino, some digital pin. Okay, then we go out here and we connect to what's called our pull-down resistor. And in this case, we're going to use a 10 kilo ohm resistor, and then this one connects us to ground. So 10 kilo ohm resistor connects us to ground. Then we go out here and we have our switch, and then our switch connects us to 5 volts. So we talked about previously how this kind of mitigates our noise issue, where if we don't have anything connected to it, we're not going to get a lot of interference, and it's going to know that we have a reference to ground. So we know exactly what 0 volts is. And if we're getting 5 volts, then we know for sure that it's not 0 volts and that we're not going to get this floating signal. Okay, so we can do something with this that's called an equivalent circuit. So a couple of things that we need to mention first. This digital pin is acting as an input right now. And so an input, we can model an input as ground, or the low potential side of our circuit. So we have this low potential side, and so we're going to model this as ground. I'm going to redraw this really quick, and then I'm actually going to redraw it again to make it easier to do a little bit of analysis on it. So we can model this as ground, and that's what we're going to do. Then we have our switch out here, plus 5 volts there. Great. Let's change this around a little bit, and we're going to draw the diagram in a slightly different way. So I'm going to draw it from the top down, and I'm going to put 5 volts here. Now in this case, we have an open circuit. I'm going to go ahead and draw it as an open circuit so that we can see what this would look like. In this case, we have no path for current to flow, right? We have 5 volts, but we have nowhere for 5 volts to go. It can't just jump this gap. It has to have some connection there. We'll draw the rest of the circuit really quick. Whoop. Want a different color. Great. Doing this. And now this is where we can, in electronics, we like to assume that we have perfect circuits. And we say, okay, our wires, for the sake of argument, we're going to say they have 0 resistance. But that's not true. Our wires do have a little bit of resistance. And remember, we measure resistance in ohms. So in this case, when we're looking at this circuit here, this whole set kind of has some resistance, but I'm just going to model that and say, okay, we have a resistor here, and maybe this resistor down here was our 10 kilo ohm resistor. And this resistance, even though it's, we like to say that wires have no resistance, in reality, they do have a little bit of resistance. So we're going to say that this one is 1 ohm, just for the sake of argument. It's probably pretty close. Wires generally have, I think, a resistance of something like 10 ohms per meter. But yeah, we're going to model this as 1 ohm and say that we have a very small resistance there. And so that in that case, I'm going to model these together. This is ground and this is ground, meaning they both are technically connected to each other. So we're going to draw it the same way there. So I'm going to put 2 connections here and then put them both to ground. So this 1 ground with 2 paths is the same as these 2 grounds with their separate paths there. Ground is ground. It's all the same thing. It's all connected. It's just an easy way to reference it on a diagram like this. So we're going to put it in a single ground here. So I'm going to draw 2 resistors And again, the reason I'm drawing 2 resistors is we like to say that this wire has no resistance, but it does. We're going to model this as our 1 ohm resistor here, and then this one is our 10 kilo ohm, 10,000 ohm resistor there. And we do have an open circuit, but if we say, all right, let's close that switch. Now we have a closed circuit. We can do some circuit analysis now. We have some path for current to flow. If you have seen my previous video on parallel and series circuits, this little notation here will look familiar to you. And we're gonna solve each side of this circuit. So we know we have 5 volts here and 5 volts there, and we know in parallel circuits that we have a voltage drop, a single voltage drop across the whole layer here. And so that means we know that this resistor here has to take away 5 volts. And this resistor also has to take away 5 volts. That's how it works in these parallel arrangements. Okay, so remember we have Ohm's law, V equals IR, and we need at least 2 of those to solve for the third. We know we have a voltage drop of 5 volts, so we can say our voltage here is 5 volts. On both sides, we actually have a voltage drop of 5 volts. So V equals 5 volts. Our resistance in this case is 10,000 ohms. And again, I'm just going to draw that as 10K. So R equals 10 kilo ohms. On this side, we know we have 1 ohm of resistance. I'm going to draw 10K here. Oh, that was pretty messy, but that's all right. 10K, 1 ohm here. So we know we have 1 ohm. R equals 1. Now, on each side, we just have to solve for our current. So we can say, well, what is our current? All right, let's solve for it. Relatively straightforward here. It's just 2 sets of Ohm's law. V equals IR. On this side, V equals 5. We're solving for our current, and our R is equal to 1. So now we can just divide both sides by 1. 5 over 1, those 2 cancel out. I equals 5. And this is measured in amps. 5 amps of current running through this 1 ohm resistor. Since it's 1 ohm, really small resistance, not going to heat up very much. Cool. Same thing with the other side. I'm going to do a little boundary separating us here. So V equals IR, V equals IR. Our voltage on this side is 5 volts. Same thing. We're looking for our current, and our resistance is 10,000 ohms, 10 kilo ohms. Divide both sides by 10,000. That cancels out. 5 over 10,000 equals I. So that means I equals 0.0005, I believe. It might be 2 zeros. Nope. 0005. Yep. 5 ten-thousandths. Current, 0.005. All right. There is this law that if we have current going through a circuit, then that current has to be the same at the beginning and the end. And so that means let's find our total current through this entire circuit. So we know through one resistor we have 5 amps. Through the other resistor we have 0.0005 amps. So we can add those together. Our total current, 5.0005 amps running through this whole thing. So if we were to measure here and we were measuring our current, I equals 5.0005 amps. Same thing right down here at the bottom. If we were to measure 5.0005 amps. But if we were to measure through each resistor, this one's getting 5 amps, and this one's getting 0.0005. So all our math adds up there. If we were to measure this entire thing for current, it's the same as the beginning and the end. So last step here, and this is how we can tell what our current is, and now we know our voltage and our current and everything going through each of those resistors. But a good double check step here is to look at our equivalent resistance. So if you have seen before, if not, you can, I think it's in another video there, but I'll just explain. If we have a resistor like this in series or in parallel, in this case we have parallel, so I have resistor, and then they connect to each other, we have an equation that tells us the equivalent resistance. So instead of modeling it like two resistors, we can model it like a single resistor. Instead of two resistors. And that equation is 1 over R PE, and I'm going to say parallel equivalent resistance is all that I'm notating that as, is 1 over R1 plus 1 over R2 plus ... 1 over Rn. So however many resistors you have, you just keep adding them in that same fashion. In this case, we only have two resistors. Fairly straightforward. We can just do some math here. So we know what our resistors are there. So 1 over, we're going to say 1 ohm plus 1 over our 10 kilo ohm, which is 10,000 ohm, equals 1 over our parallel equivalent resistance. A little bit more math. 1 over 1 is the same as 10,000 over 10,000. Remember, we have to have the same denominator if we're going to add them together. Plus 1 over 10,000 gives us 10,001 over 10,000. But this is not our equivalent resistance. It is 1 over our equivalent resistance. So we have to take the reciprocal, which is the whole thing to the power of -1, or just flip it over. Flip the numerator to the denominator. So if we take this to the -1, then we're going to get our equivalent over 1. And anything over 1 is just itself, right? Cool. So 10,000 over 10,001 is equal to 0.9999 ... I think there's a bunch of zeros here. But we're going to use 4 nines, 0.9999. And that is going to be our equivalent resistance. A good rule here, if your equivalent resistance comes out and it is higher than any of your resistors, you did something wrong. Your equivalent resistance has to be lower than the smallest resistor in the entire parallel circuit. For parallel, anyway, that is true. And in this case, remember we had a 1 ohm resistor and a 10 kilo ohm resistor. So our 1 ohm is our smallest. This one is just barely smaller than our 1 ohm resistor. Checks that off for us. That's correct. So that is our equivalent resistance. Now, instead of modeling it like that big parallel thing there, we can just model it as a single resistor that comes down to ground. And that resistor has a resistance of 0.9999. We know that we have 5 volts. And this is just double checking our total current here, because now we have our voltage and our resistance. Through Ohm's law, we can find current. V equals IR, where I is current, V is voltage, and R is resistance. 5 volts equals some current I times our resistor, 0.9999. If we do the math on this, divide everything by 0.9999. Those cancel out. 5 over 0.9999, 5.0005 amps. Which, if we look, 5.0005 amps. When we made our equivalent circuit, same exact thing as right here where we did all our calculations, 5.0005. So we know for sure that is the current going through our entire circuit. We've double checked ourselves by making an equivalent circuit. We could do either of these steps first. So if you see this and you say, oh, well, I want to figure out my current first and then figure out how the current is divided up, instead of figuring out the divisions of the current and then adding them together, you could do this step first. You can say, okay, I'm going to make an equivalent circuit. And then through that equivalent circuit, I know my current, and I'm going to divvy it up by 1 over 10,000 versus 10,000 to 1. And that's, you can do the math there, and it all works out the same. So that should kind of give you an intuitive understanding of this circuit that is splitting our current. And this is a current divider circuit. So that is why we can model this circuit right here as a very small resistance right here. And remember, through our 10 kilo ohm resistor, we had very, very little current going through here. So even when this is all complete, the current that's going through this side is 0.0005 amps of current. And this one has about 5 amps of current, which means the vast majority of our electrons are going into our digital pin. So our digital pin sees that, and it's floating up there around our high voltage. And when that's closed, then all it can see is ground. And because all it can see is ground, again, floats down here next to ground, instead of having this kind of ambiguous thing. So that's the calculations for our current divider. In a future video, we're going to go over potentiometers and what they're used for and how to calculate potentiometers, which are a voltage divider instead of a current divider. All right. Thanks for watching this video. If you have any questions, send them to me. I have some other videos linked in the description. Yeah. Thanks for watching.